Okay. So I say I have a function f of x, say something like that, from A to, I guess, shorten it up a little bit. Function f of x, say, from A to B. So here's f of x. Okay. What we're going to be looking is what's referred to as arc length. Um, GTH. So arc length also, or you could say length of the curve. Okay. So the length of the curve means if I was to start at A, f of A, and follow the curve like a road, what distance did I travel? Okay. You could also think of it as like if this is a piece of string, you would pick it up, stretch it straight, and measure it. That would be arc length as well. So we're trying to get the length of the curve like that. Okay. So how could we estimate this length? Well, one way to estimate it is, as you probably guess, we'll divide the x-axis into some number of intervals, n intervals, say. So divide it into n intervals. And let's say we'll pick say this is xk, and this would be xk plus 1. So and what we'll do is we'll plot those 2 points. And what we're going to do is connect the lines like that. Okay. So if I do that for every one of these, and then from here to here, here to here like that, there to there, there to there, maybe from here to here and here to here. Those are all straight lines between 2 points. You might recall the distance formula from earlier classes. If you're given a point x1, y1, and a point, say, x2, y2, and you plot them, you want to compute the distance between the 2 points. Remember that what it was the distance was the square root of the change in x, say x2 minus x1 squared, plus the change in y2 minus y1 squared, right? That's the ordinary distance formula. So if I break up these, if I break into these little intervals, plot each point on the curve for the intervals, compute the distance between each point, I get a pretty good estimate of the actual length of the curve, the distance traveled across the curve. Okay. And obviously, if I make it, if I divide it into narrower intervals, I get shorter distances, but when you add them all up, you get a better estimate. So suppose I just, for grins, let's look at this part. I'll kind of explode this part right here. So I'll go down here and say there's a point there. There's a point there. The curve's going like this. And that's supposed to be our straight line. Okay. So this would be the point x1, or xk rather, xk, comma, f of xk, right here. And this would be the point xk plus 1, comma, f of xk plus 1. Okay. So this distance right here, we'll use that formula. We'll say, okay, the distance, I'll call that d. The distance is going to be the square root of the change in the x's, which would be xk plus 1 minus xk, and all that would be squared. And then I would add to that f of xk plus 1, which would be like yk, I guess you could call it. Minus f of xk. And of course, all that would be squared. And it's under the square root. Okay. So realize what I'm doing is if I was to drop this like a vertical line down here like this, and one over here, this would be your change in x, which we'll call delta xk. Delta xk, you see, is equal to xk plus 1 minus xk. So I can rewrite d this way. So xk plus 1 minus xk is the same thing as delta xk, so we'll call that delta xk squared. And then this point here, see, this is f of xk plus 1. This is the same y value as this point, which is f of xk. So we would call that delta yk. Okay. So b plus, this is now delta yk squared. So there's two ways to write the same formula. Okay. So again, let me draw this little piece again. I'll draw it like right about here, there. There's my straight line. And my curves moving like that. Okay. So let's remember a theorem from Calculus 1. Theorem called the mean value theorem. Anybody remember what that theorem says? And does anybody remember hearing about it? Okay. Yep. Kind of. So someone says, there's a point that the derivative exists. That's true. There's a little more to it than that. The mean value theorem says something along the lines of if if f of x is continuous on an interval I think they use AB, but it could be anything. And I believe it also says and differentiable on open AB, then there exists at least one number C such that f prime, the derivative at C, is equal to f of B minus f of A over B minus A. Okay. So what that's saying is, if I have a continuous curve on an interval, it's differentiable on at least the open interval, then there should be at least one number such that if I take f of B minus f of A over B of A, which is essentially the slope of that line, right? That's a change in y over change in x. So it's a slope of that line. Then there's one number f prime, one number C somewhere between A and B that the derivative is equal to that slope. So remember, what is the derivative? The slope of the tangent line. Okay, so what they're saying is somewhere along the x-axis, there's a point here that we'll call CK, if you want. I'll call it XK star. XK star, such that if I plug in if I plot it up here, its slope of its tangent line is parallel to that distance, parallel to this distance point. Okay. So if I apply the mean value theorem to that distance formula, what it's saying is that, because remember, this is, oops, how did I do that? Remember, delta yk over delta xk is the slope, right? So according to the mean value theorem, if I take delta yk and I divide that by delta xk, then there exists some point between xk and xk plus 1, which I'm just going to call xk star, such that the derivative of xk star is equal to this. So in other words, the derivative of xk star is the slope of the curve, the slope of the tangent line to the function at the point xk star. And that slope is the same as the slope of this distance that connects the 2 points. So what does that do for me? Okay. Since that's true, I can rewrite delta yk to be f prime of xk star times delta xk. Right? So delta yk equals that. Okay. Which means now in this formula up here, instead of saying delta yk squared, I'm going to insert all this. So in other words, my distance formula, which originally was this, delta xk squared plus delta yk squared, can now be written as the square root of delta x squared, xk squared, plus, and then where I have delta yk here, I'm going to put all this. So I'm going to have f prime of xk star delta xk, and then all of that squared. So it's two equivalent ways to write the distance formula. but the one on the right is going to be more useful. So the question becomes is how will that be more useful? So what I'll go ahead and do is rewrite it now. Let's see here. Delta xk star, delta xk squared plus, now I've got two things multiplied and they're squared, so that means I can square the first thing, f prime of xk star squared times delta xk squared. I'll put parentheses around it. Okay. So notice now I can rewrite the distance as, what I'm going to do is I'm going to factor out delta xk squared from both of these terms, which will mean inside I'd have a 1. Then I would have a f prime xk star squared delta, I'll put a parenthesis here, delta xk squared. I'll put square brackets like that, so sometimes that makes it clearer. So basically, I factored delta xk squared out of these two terms, and then what's left inside is 1 plus f prime xk star quantity squared. Now, the square root of delta x squared is just delta x. So I'm going to rewrite this. I'm just basically taking the delta x squared out from under the square root and rewriting it like this. 1 plus f prime of xk star squared, and then outside I just have a delta xk. Okay. So remember that distance formula is just for one little piece, right? It was just this piece right here. So now I can do that. I can use that same distance formula for each one of these segments based on the intervals. So what am I going after here? I'm going to go after a sum, and what do we call that type of sum? Named after a German? Yes, the Riemann sum. So the length is approximately the summation as k goes from 1 to n of this distance formula. 1 plus f prime of xk star, then all that's squared, delta xk. So in other words, I said k 1, 2, 3, 4, 5. It's essentially that summation is adding up all these pieces, right? It's adding up that distance, that distance, that distance, that distance, that distance, that distance, that. Good. So that gives us an estimate for the arc length. It's not perfect. To get the obvious, just like every Riemann sum, the bigger n is, the better the estimate is. To get the exact answer for the length, I'm going to take the limit as n goes to infinity of this summation. The square root of 1 plus now a star squared delta xk. But remember, the limit of a Riemann sum turns the formula into a definite integral, right? So that means L is now going to be the integral from a to b of the square root of 1 plus f prime x, right? Remember, wherever you see an xk star, you change it to x. So it's f prime x squared, and then delta xk turns into dx. So that's our formula for the length of a curve. We just derive that formula. All right. So now let me do another share here. Yep. Continue. And screen. So let's see if I can find the one I want. Maybe this will do. So this is how a textbook does what we just did. So basically, here's your curve. Here he's dividing into n subintervals, and connecting, labeling them and then connecting the points, and saying adding the points would estimate the curve. So this is the length of a kth unit, right? It looks at the picture of the kth unit, and then based on the mean value theorem, you can rewrite the delta y and the f prime. He uses ck instead of xk star, but it's the same thing. Factors it out, does the limit. Here's your formula. So the formula reads, definition, if f prime is continuous on AB, then the length or arc length of the function y equals f of x from the point A, which would be A, f of A, to the point B, B, f of B, is given by this integral. L equals integral A to B of the square root of 1 plus f prime x squared dx. And f prime x you can also write as dy dx. Okay. So let's work this example. I'm going to go back to the whiteboard so we can manually work it. Documents, whiteboard. All right. So the function in question is, it's under Acrobat actually. So y equals 4 square root of 2 over 3, x to the 3 halves minus 1. All right. So what we want to do, the question will be, all right, what's going on here? Find the length of the curve let's see how he says it exactly. Find the length of the curve given by y equals 4 root 2 over 3, x to the 3 halves. So given by 4 root 2 over 3, x to the 3 halves. That's 3 halves power minus 1. And what were the bounds? From 0 to 1. 4 root 2 over 3, x 3 halves, from 0 to 1. From x is greater than or equal to 0 to less than or equal to 1. So when I want to find an arc length like this, I'll write the formula down. I like to write it down. The more I write it down, the easier it is to remember. It's the integral of a to b, square root of 1 plus f prime x squared dx. Okay. So in this case, y is f of x. So f of x here is 4 root 2 over 3, x to the 3 halves, minus 1. Okay. So what we do is we think of the formula as an algorithm. The formula tells us what to do. Inside the formula, notice I have f prime x. So first thing I got to do is compute f prime of x. So the first derivative of this function would be 4 root 2 over 3 times x to the 3 halves would be 3 halves x to the 1 half. And then derivative of 1 is 0, so I have to put anything there. And you could rewrite it slightly, because notice the 3's cancel, and 4 cancels with 2. You give a 2. So all I got left is 2 root 2 times x to the 1 half, which is root x. Everybody agree with me on that? Okay. So I could rewrite this as 2 root 2x. Okay. So that's f prime x. What does the formula tell me to do with f prime x? The formula says once I got f prime x, what do I do with it? Answer is, someone said, yeah. Answer is square it, right? That's the next thing. So now I got f prime x, I got to square it. So that's 2 root 2x squared, which is going to be 4, or 2 if you want, 2 squared root 2x squared, which we're just going to use the positive root 2x squared. So that's going to be 4 times 2x, or 8x. Okay. And what's the next thing the problem says to do? The formula says to do. Once I got fx squared, it just says add 1 to it. So now 1 plus f prime x squared equals 1 plus 8x. Then the formula says we're going to put that under a square root and integrate it from a to b. And in this case, a to b was 0, 1. So the integral we have to do that one. Okay. And that 1 plus 8x comes from doing the parts of the formula sort of individually by saying, okay, well, f of x is, let's see, I'll cover it up. At least I'm covering it up for me. F of x is 4 root 2 over 3, x3 has minus 1. Compute f prime x, get 2 root 2x. Square it, get 8x. And then add 1 to it, 1 plus 8, and that's what goes under the square root. So now doing this integral is not too hard because it becomes the integral 0, 1, take the square root, write it, instead of square root, write this to the 1/2, and then dx. Okay, so what does this what's the antiderivative here, for this definite integral? How do I integrate 1 plus 8x to the 1/2 dx? Anybody want to? What would you get? Well, we have to, we'll use U substitution essentially for power rule, right? So here we're going to say U equals 1 plus 8x. Therefore, du equals 8 dx. So to use that power rule, I need an 8 there. So that means I can take the same integral, multiply it by an 8, because the reciprocal of 8 is 1/8. Integral 0 to 1 of 1 plus 8x to the 1/2, and then you have to have 8 dx. Okay. It's the standard power rule. So that means the 1/8 carries through to the answer. Something to a power times its derivative is the something. Times power plus 1 over power plus 1 from 1 and 0. So we're going to clean that up a little bit. This will be 1/8 times, this is 3/2, so this would be 1/8 times, if you're over 3/2, same as multiplied by 2/3, 1 plus 8x to the 3/2. Okay. And we can clean it up, of course, from 1 to 0. We can clean it up a little bit, because this 2 can go into become a 1, and that becomes a 4. So now I've got 1 over 12. 4 times 3 is 12. 1 plus 8x to the 3/2 from 1 and 0. So if I plug in 1, I get 1/12. I get 1 plus, right, 8 times 1 to the 3/2, minus plug in 0, I get 1/12, 1 to the 3/2. So this becomes, that's a 12 there. Right? This becomes 1/12, 9 to the 3/2. Because 8 times 1 is 8 plus 1 is 9, minus 1/12. 1 to the 3/2 is 1. So I could factor 1/12 out of here, and that would leave me with 9 to the 3/2 minus 1, which means I have 1/12. What's 9 to the 3/2? Somebody work that out for me. Anybody come up with that? $27. Yep. 9 to the 3/2 is 27. So you're going to have 27 minus 1, which would be 27 minus 1 is 26. You get 26 over 12, or 13 over 6 would be your arc length. Everybody good on that? So really sort of the process I did was, first of all, identify what f of x is, what the bounds are, and then do what the arc length formula told me to do. First thing I got to do is get f prime x. So I get it. Formula says once you got f prime x, square it. So I squared it. And squaring this gave me 8x. Once I have that, I add 1 to it because that's what the formula says to do. And then that's what I'm going to integrate, the square root of that from 0 to 1. And then I just go through the standard method of integrating it. This is a little side note. Another way you can, so it's really the way I do U substitution, the way a lot of other people do it. I'll just show you that. They're logically equivalent. So if I go back to this problem, so what we do is we say, okay, suppose U is 1 plus 8x, and we know du dx, if you want, is 8. So what is dx? Well, that implies dx is du over 8. So that means I can rewrite this integral 0 to 1 of the square root of u du over 8. Right? So I'm writing the integral in a new variable, which means the integral can now be written du over 8, same as 1/8 times du, so you can factor this out. 1/8. You could go u to the 1/2 here, du. Now, I've changed the variable from x to u by this substitution right here. Okay. So I can't use the same bounds because those bounds assume, in fact, I should erase them from there. Those bounds assume that the variable is x, but the variable is u. The variable is really 1 plus 8x, right? So what I do is I say, okay, well, wrong mode there. If I say when x equals 0 in the original problem, u equals 1 plus 8 times 0, or 1. So u0, when x equals 0, translates to u equal 1. Okay. And then when x equals 1, u equals 1 plus 8 times 1, or 9. So when x is 1, the integral in u is 9. Okay. So this integral here will generate the same, this integral here will generate the same answer as that integral there. But this is easy to do because now, see, if I have 1/8 integral 1 to 9 of u to the 1/2 du, u to the 1/2 du integrates to 2/3 u to the 3/2, and then of course still have a minus 1/8 here, carried through the answer, from 9 and 1, which is 1 over 12 u to the 3/2 from 9 and 1, because 2 cancels with that guy, gives you a 4. Right? 4 times 3 is 12. So now you just plug in 1/12 9 9 to the 3 halves minus 1/12, 1 to the 3 halves. And you can see, when I did it my way, I got that same result, right? 1/12, 9 to 3 halves minus 1/12. Okay. That's why I say the two methods are really logically equivalent, because I know some people teach it like I do, especially us older guys, and other people tend to do it this way. I think books now tend to do this. You know, rewrite it as you and then integrate it. Whatever works for you is fine with me. Okay, because you're going to get the same answer if you do it right either way. Mm-hmm. Any questions on that? Okie dokie. Let's look at another one here. X cubed over 12 plus 1 over x. So the question here is, find the length of the graph of, actually I think I use f of x here. F of x equals, where was I? F of x equals x cubed over 12 plus 1 over x, 1 to 4. And x is between 1 and 4. So x cubed over 12 and 1 over x. Okay. So again, the easiest process. If you want, you can write the formula down again. Square root of 1 plus f prime x squared dx. And then do what the formula says to do. So the formula says find f prime x. So f prime x for this f of x would be 3 x squared over 12 plus minus 1 over x squared, right? Because that'd be x to the minus 1, so minus x to the minus 2. Okay, so in other words, 3 over 12 cancels with 12, gives you 4. So you have x squared over 4 minus 1 over x squared. Okay. What's the formula say to do next? And the answer is, you got to square that derivative. So f prime of x squared now is what you have to do now. Okay. Right. So you're going to square this binomial. X squared over 4 minus 1 over x squared squared. So remember, the way that works is you square the first term. Right. And it's minus 2 times the first term times the second term. And then you add to that the square of the second term. and then you do some cleanup. Okay. So f prime of x squared equals the first term squared. So x squared squared would be x to the 4. 4 squared would be 16. So you have x to the 4 over 16. Here, notice your x squares cancel, right? And 2 over 4 is a half. So you just end up with minus a half here. And then 1 over x squared squared, 1 squared is 1. And x squared squared would be x to the 4th. Okay. So that's f prime x squared. Now remember, what I got to do to it is add 1, and I got to put it under square root. So it would behoove us to maybe rewrite this. So let's go ahead and do this subtraction addition with a common denominator. Okay. So that means the common denominator here between 16(2) and x4 would be 16x4. Because 16x4, if I multiply x4 by 16, I get 16x4. 2 divides evenly into 16. So I don't have to make it the number any higher. Okay. So then what did I have to do to this 16 to make it 16x4? And the answer is multiply by x4. So I got to multiply top and bottom of this first fraction by x to the 4th. So the x4 times x4 is x8, right? So that's the first term. What did I have to do to 2 to make it 16x4? I had to multiply 2 by 8 to get the 16 in the x4, so the top becomes minus 8x4. And then I have to multiply top and the bottom here by 16 to make x4 16x4. My x is not looking good there. So that means I'm going to add 16. Okay. So now I've just rewritten f prime x squared into a little cleaner looking fraction, because the next thing I have to do is add 1 to it. Right? That's what the formula says to do. So that's going to be 1 plus this whole fraction, x8 minus 8x4 plus 16 all over 16x4. Okay. All right. All right. However, how many different ways can I write the number 1? Well, the answer would be infinite, but I'm going to write it a particular way. I'm going to write 1 as 16x4 over 16x4. And then I'm going to add that to this guy. So why do you think I chose to write 1 as 16x4 over 16x4? And you're probably saying, well, because I want common denominator of that fraction in 1. So there's my common denominator. So then Now you see I can write this all over one denominator. And then I have this here, 16x4 plus x8 minus 8x4 plus 16. Okay. So notice now 16x4 and minus 8x4 could turn into plus 8. I can combine these two terms. So now I have this. So it'll all be over 16x4. Okay. And then, so the first term is now x8. 16x4 minus 8x4 becomes plus 8x4. So there's my 1 plus x squared. So the bounds of my integral are 1 to 4. So my length is given by the integral 1 to 4 of the square root of that whole thing. Okay, dx. Now, when I first did these and learned these in college, I probably had the same reaction you're having right now. It's like, good Lord, how am I supposed to integrate? That's a crazy looking thing. But it turns out, if I take this function here, notice 16x4 can be written as 4x squared, the whole thing squared, right? Because 4 squared is 16, x squared squared is x to the 4. Believe it or not, the top is factorable. Okay. If you factor the top, you end up with x4 plus 4, the whole thing squared. Because the first term, x4 squared is x8. Then you have, if you wrote x4 plus 4 times x4 plus 4, and you did a FOIL method, you get x8. Then you'd have 4x4 plus another 4x4, that'd be 8x4. And then you'd have 4 times 4, which is 16. Okay. And remember, if you have a fraction where the top and the bottom are both squared, you can just write the numerator okay, divided by the denominator like this, and square the entire fraction. Okay, because a over b quantity squared, same thing as a squared over b squared. So we're applying that. So now, once I know I can write it that way, you feel a sense of relief because all of a sudden now this thing's way easier to evaluate. Right. So the square root of something squared just gets rid of the square root, right? Now this is your integral. Good. Now, it still maybe looks a little daunting, but it's really not that bad once you recognize, well, 4x squared is the common denominator for each one of these terms. So I can now write this as, you know, x4 over 4x squared plus 4 over 4x squared. Well, x4 over x squared is x squared, so this now becomes x squared over 4, just because the x4 canceled the x squared, left in x squared. And then I got 4 over 4x squared, so the 4 cancels, I get 1 over x squared, and 1 over x squared is the same thing as x to the minus 2. Now I've got something that's fairly easy to integrate. So just realize this expression and this baby up here are algebraically equivalent. And which would you rather work with? This down here or that up there? You want this down here because you can do it. Up here, you can't really do it. So that means the integral of x squared over 4 would be x cubed over 12, right? Because it would be x cubed over 3, and 4 times 3 is 12. X to the minus 2, if you integrate that, it's x to the minus 2 plus 1 over minus 2 plus 1, which would be x to the minus 1 over minus 1, which would be minus 1 over x. So you get this. That's your antiderivative. Plug in 4 and 1, and you get your length. So if we plug in 4, we get 4 cubed over 12 minus 1/4. We can think of 4 cubed as 4 times 4 squared. You could think of 12 as 4 times 3 minus 1/4, and then lo and behold, they cancel. So 4, well, so you got, so this becomes 16, 4 squared is 16 over 3 minus 1/4. You then get the common denominator of 3 and 4, which is 12, right? So you had to make 3 12, you had to multiply by 4, so you got 16 times 4 minus, to make 4 12, you had to multiply by 3, so you have minus 3. So this would be over 12. 16 times 4 is what? What's 24 to 64 minus 3 be 61 over 12. What's 61? 3 times 21. And 12 is 3 times 4. So you can cancel those, and you get 21 over 4. That's my arc length. Okay. Did I even get that? Oh, I must have messed up something somewhere. Or did I? Let's see here. I plugged in 4. And now we get, so the answer is x squared over 4, 1 to 4, 1 over x squared. So I got that right. So I just messed up arithmetic somehow or another. Let's see here. So I'm good up to here. 4 cubed over 12 minus 4, minus 1/4. Oh, I didn't subtract the 1, did I? That's where I went wrong. Sorry. So here I plugged in 4. I'll go ahead and take this off too. But I neglected to then go minus parenthesis, now plug in 1. 1 cubed over 12 minus 1 over 1. All right. So now let's see what we get. So this would still be 4 squared. This would be 4 times 4 squared, and 4 cancels 12, get 3. So I get 4 squared, or 16 over 3, minus 1/4. This would be minus 1 over 12. And then minus and a minus becomes plus 1. Okay. So now we got to get a common denominator here is going to be 12. 3 goes to 12 4 times. 4 times 16 is 64. Right? 4 goes to 12 3 times. I get minus 3. 12 minus 1. And 1 is 12 over 12. So now I've got to move down here and so let's see, this would be 60 plus 12, right? Because that would be minus 4 plus 64 would be 60, and then plus 12, so you get 72 over 12. So what's that? 6. There you go. 6 whatever units is the length of that curve. Okay. Which means this integral right here, it's another way to write the number 6, if you care. Any questions on this? What you probably notice in here is, darn, this stuff, it's a lot of algebra, depending on the function. And when you take its derivative, its squared, all that, you can get a lot of algebra to get to the final answer. Okay. So you just have to grit your teeth and bear it and work the algebra till you get to an integral that you can integrate. It's just the nature of this particular beast. And here's the other thing. There aren't all that many problems we can do until we learn some more integration techniques, which is, the topic after these applications. And so typically what I do when we learn more techniques, I'll give you problems, more arc length problems that's the integral is integrated with these new techniques, but that's for the future. Okay. All right. All right. Let's look at another one. All right. Suppose I want to make it a little more room. Any questions up till now? Okay. Let's do the following. The next example I'll do is find the length of the curve. And what was the curve? Y equals e to the x plus e to the minus x of the curve. Y equals, I think it was 1/2 now that I think about it. Let's see. Yeah, 1/2 e to the x plus e to the minus x. 1/2 e to the x power minus or plus, was it e to the minus x? Plus, yeah, e to the minus x, and then from 0 to 2. And 0 less than equal x less than equal 2. So again, write the formula. 0 to 2 pi, 0 to 2 rather. Sorry, I like the general formula. A to B. 1 plus f prime x, the whole thing squared, dx. Okay. So again, what's our f of x? All of this, right? So f prime x is going to be 1/2. What's the derivative of e to the x? Answer, e to the x. What's the derivative of e to the minus x? Answer, minus e to the minus x. So that plus changes to a minus. So that's f prime x. Now, what is f prime x squared? Well, it's going to be 1/2 squared, which is going to be 1/4. Okay. And then you're going to square this binomial. You take the first term squared. So e to the x squared is e to the x quantity squared, right? But another way to write that, if I have something to a power, I just multiply the powers. So e to the x squared is really e to the 2x. So we're going to change that to e to the 2x. So I'm going to have, e to the 2x. Then I have to go minus first times second. Minus 2 times first times second. Okay. And then we're going to add to that e to the minus 2x, or e to the minus x squared. Okay. So let's simplify this a little bit. Okay. This is e to the 2x. What's minus 2? What's e to the x times e to the minus x equal to? Somebody type me an answer to that one. What's e to the x times e to the minus x? 1, correct. So it's just 2 times 1, or 2. And I'm going to write e to the minus 2x is 1 over e to the 2x. All right? Okay. So now I've got these 3 terms. The one's a fraction, so I want a common denominator for that. The common denominator will be e to the 2x. So to make e to the 2x over 1, I have to multiply top and bottom by e to the 2x. So e to the 2x times e to the 2x is e to the 4x. Right? 2 over 1 would be 2 e to the 2x. Oh, minus 2 e to the 2x. E to the 2x. And then that one I didn't have change. If I multiply this by 1/4, I just get over 4 e to the 2x. So so that basically that's how I want to write f prime x quantity squared. So I did it up here, I just squared the binomial. So square of 1/2 is 1/4. The square of e to the x minus e to the minus x is this. And then I simplified this to look like that, right? And then it's 1 fraction and 2 not fractions, so I have to make the common denominator that e to the 2x, and then adjust these accordingly. And that's what I have, and then I multiply 1/4. Okay. But the formula says I got to take whatever that is, add 1 to it. So now I have to have 1 plus f prime x squared, which is now going to be 1 plus all of this. Right? Plus 1 all over this. Well, again, to add 1 to this fraction, I need a common denominator. So the common denominator is going to be 4e to the 2x. So the way I'm going to write 1 here is 4e to the 2x over 4e to the 2x. So this becomes 4e to the 2x over 4e to the 2x plus all of this. So now 1 plus f prime of x squared is all going to be over 4e to the 2x. I'll start with e to the 4x. Now I've got 4e to the 2x minus 2e to the 2x. So 4 of something minus 2 of something leaves me plus 2 of something. 1. Okay. Now, so now what do we have to do with this? According to the formula, we have to take the square root of it and our bounds and integrate it. So according to the formula, the length is going to be 0,2 of this stuff square root of all that. So it looks nasty, but just like before, these are both perfect squares. So what you're going to have is the integral of 0 to 2. See, if you think e to the 4x could be written as, see, e to the 4x, it's the same thing as e to the 2x squared. So I got e to the 2x squared plus 2e to the 2x plus 1. That means that's going to be e to the 2x, be careful there, plus 1 squared. If I take e to the 2x and square it, I get e to the 4x, and I get plus 2 times e to the 2x times 1, which would be 2e to the 2x, and then plus 1 squared. The bottom is just 2 e to the x squared, square root. Okay. So now the length becomes the integral of 0 to 2. So the square root of e to the 2x plus 1 squared is just going to be e to the 2x plus 1 divided by 2e to the x quantity squared. Square root is 2e to the x. So this now is a nice or an integral to do, because just like the previous example, 2e to the x is a common denominator of e to the 2x and 1, so I can write this as e to the 2x over 2e to the x. Okay. And then I can just write plus 1 over e to the x. But 1 over e to the x is really e to the minus x, so let's write it that way. Okay. Well, we'll write it that way, because I want to do one more simplification step. So just remember that. what is it? 1 over 2 e to the x, right? That's not clean. Hang on. Okay. 2 e to the x. All right. I'll do that right. 2 e to the x. Yeah, squared. So that's our integral. Now, and simplify it one more time. E to the 2x over e to the x is just e to the x. So I'm going to have e to the x over 2. And then this thing is going to be plus 1 over 2 times e to the minus x. I'm going to take the e to the x in the denominator, take it upstairs. So I get this. And then here I can factor out a half. So I get 1/2 integral 0 to 2 of e to the x plus e to the minus x. That means the length is now 1/2. The integral of e to the x is e to the x. What's the integral e to the minus x? Just the antiderivative e to the minus x. Well, it's e to the minus x with a minus in front of it. You can check that. Did you get this? And then you got to put in here 2 and 0. So if I plug in 2, I get 1/2 e squared. And I'm going to write that as e to, well, let me do one more step. Because I like to get rid of negative exponents when I can. So this is 1/2 e to the x minus 1 over e to the x. Is e to the minus x, 1 over e to the x. 2 and 0. So the length now is going to be 1/2, plug it in 2, e squared minus 1 over e squared. Subtract from that 1/2 e to the 0 minus 1 over e to the 0. Okay, so now this is 1/2 e squared minus 1 over e squared. What's e to the 0? Well, it's anything to the 0. It's 1, right? So this is 1. This is 1. 1 over 1 is 1. So you got 1 minus 1 or 0. So all of this is 0. So that's my answer right there. I could write it as 1/2 common denominator is e squared. So I'd make that e4 minus 1 over e squared. And then you could write e4 minus 1 over 2e squared. So that's how you use the arc length formula. Unfortunately, it generates a fair amount of algebra to do. Okay. So you do have to practice these a lot. Okay. Any questions on that? All right. The next application we'll look at is surface areas. Surface areas specifically of revolution. In other words, we take some graph, we revolve it around the x-axis, say, and instead of getting the volume of the object, we get its surface area. Okay. So I'm going to just, rather than hand derive the formula for this, we'll just look at it on from a book here real quick. So is everybody good with what they saw here? I am recording this, and once the recording processes and all, I will post it in the module, in the applications module, and you can watch it and watch me do these over and over again until you can't stand me anymore. Okay. So let's change here and go screen. This one. So here, what we're looking at is the idea of, suppose I have a curve, like a line, and I rotate it around the x-axis. Okay. Well, we know that rotating around the x-axis, we can generate a solid object, and we know how to find the volume of that. Okay. So instead of finding the volume, we want to find just the area of the surface that's generated by sweeping around. So it's just the surface area rather than the whole volume. Okay. So the way you derive this is you take your curve, you say, okay, if I take my curve and rotate it around, I get this weird shape here. So I'm going to divide my x-axis into intervals. And then I'll look at one piece, which is right here. And basically what he wants to get is this line, and then multiply that, make that the height of a circumference. So the circumference would be 2 pi a radius, and then times this length, okay, times that distance right there, okay. So what he says is they want to take a point xk plus minus 1 and xk. He's going to say the length, he's going to go 2 pi, and then he's going to do f of xk minus 1 plus f of xk over 2. Well, that's the midpoint. If the function f of xk minus 1 is this p, and the function f of xk is this q, f of xk plus 1 divided by f of k is, the midpoint between p and q in that height. So he's going to say use that as the radius of a cylinder. So he's going to say, what is its circumference? He's going to use that average height as the radius of a cylinder, and then take the circumference, 2 pi times that radius. So that's where this 2 pi times that radius comes from. He's then going to multiply it by that distance, okay, from P to Q. That's what this delta xk squared plus delta yk squared, so forth, okay. Then he notes, well, I got 2 pi times something over 2. I'm going to cancel that. So he gets pi f of blah, 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 plus, pi times this sum right here times that. So he says, so he's getting an estimate of the surface area of that little strip. So if he cuts it up into a bunch of little strips and adds them up, he gets this summation. Okay. So he's going to generate a Riemann sum there. Does the same thing with, f prime of ck is delta y over delta x. So he's going to put that in for yk. So you get this. And now your summation looks like this. Pi times this sum, f of x5 over 2, times the square root of 1 plus x squared. And if he takes the limit of that as n goes to infinity, what he chose to do was go back to, so really he didn't need to cancel this 2. He should have kept it. But what he's going to do is put it back here. So you have 2 pi f of xk minus 1 plus f of xk over 2. As n goes to infinity, that just turns into f of xk, and then you have the 2 pi. So you end up with the surface area formula, the integral a to b 2 pi f of x times the square root of 1 plus f prime x quantity squared. In other words, the integral a to b, 2 pi your function, and then the rest of it's your arc length formula, right? The arc length formula just was what I highlighted there, but didn't have anything in front of it. Okay. So this is the theorem here. If you have a function f of x, which is greater than or equal to 0, and it's continuously differentiable on AB, then the area of the surface generated by revolving the graph y equals f of x about the x-axis is given by this formula, S. He calls it S. S equals the integral AB of 2 pi y square root of 1 plus dy over dx squared dx. So just realize y equals f of x. So you can write it as 2 pi y dy dx, or you can write it as 2 pi f of x, f prime x squared. I prefer the second one when I work these problems. Or you can do the first. Doesn't matter, as long as you realize they're the same thing. Okay. So here's an example. He says, find the area of the surface generated by revolving y equals 2 square root of x from 1 to 2 about the x-axis. Okay. So he's saying y is 2 root x, so he'll use 2 pi y root 1 plus dy dx squared. So again, you're going to have a formula. You're going to do what the formula says, right? What's dy dx? If y is 2 root x, dy dx is 1 over root x. I'm going to square it. If I square 1 over root x, I get 1 over x. And I get 1 plus 1 over x. Then he says, okay, 1 plus 1 over x, the same thing as x plus 1 over x, or square root of x plus 1 over square root of x. So that's going in the second half of the formula, right? So the square root of 1 plus dy dx squared, it turns out to be root x plus 1 over root x. So he puts that in there. Then he has to put 2 pi in his y. Well, what is his y? 2 root x, right here. Okay. So now he's got s equals 1 to 2 of 2 pi times 2 root x times square root of x plus 1 over root x. Well, notice the root x cancels. 2 times 2 is 4 pi, so he factors 4 pi out, cancels the root x's, and now you got 4 pi integral 1 to 2 square root of x plus 1 dx. Okay. You work that integral out, you get 4 pi 2/3 x plus 1 to 3/2 from 2 and 1. Plug in 2 and 1, you get this. So it's really a new formula, and it's a lot like the arc length formula. It has the arc length formula in it, but it has this extra term, 2 pi y or 2 pi f of x, however you want to write it. Down here is the formula, surface area for resolution about y axis instead of the x-axis. And he's just saying if x is a function of y, so he calls x as gy, is greater than 0 and is continuously differentiable on CD. So this term right here, continuously differentiable, just means a function is continuous and differentiable. Then the area of the surface generated by revolving the graph of x equals gy around the y-axis is s equals c to d 2 pi x square root of 1 plus dx dy squared dy, or c to d 2 pi gy square root of 1 plus g prime y squared. So same formula, right? It's just that this is the formula if x is a function of y, and the one up here is the formula if y is a function of x. Okay. So let's pick a couple to do here. Let's see here. Number 9. Find the lateral surface area of the cone generated by revolving the line y equals x over 2 from 0 to 4 about the x-axis. Now, check your answer with the geometric formula. So what he's saying there is you can get the answer with a geometric formula if you remember it, or you can do it by rotating. Let's do it by rotating. So let me go back to share screen, documents. Okay. So basically, I want to find the surface area of the cone generated by revolving and get it right by revolving the line segment y equals x over 2 from 0 to 4 about the x-axis. The line segment y equals x over 4. Make sure I got that right. X over 2. If I want to be consistent with it, you could do x over 4, but it's an exercise in the book, so x over 2. From 0 to, let's see, what was that? 0 to 4. Right in here. 0 less than equal x less than equal 4. Okay. So again, we'll write down the formula, the surface area, integral a to b, 2 pi f of x times the square root of 1 plus f prime x squared dx. So again, it's the arc length formula under the square root part's the arc length formula, and then you have this 2 pi and then the function. So in this case, f of x is the x over 2. So let's do the arc length part first. So I got this formula. It says I got to have f prime. Well, if x over 2 is f of x, f prime is a half. It says I got to square f prime. That'd be 1/2 squared, or 1/4. It then says I got to add 1 to it. Which equals 1 plus 1/4, which equals 5 over 4. So now the surface area is the integral from a to b, which is 0, 4. And I got to have 2 pi times f of x. Well, f of x in this case is x over 2. And then times the square root of that 1 plus f prime x squared, which is 5/4. Dx. So that's what I have to integrate. So notice these 2's cancel. So this is going to be the integral of 0 to 4. These 2 cancel, so that gives me pi x. The square root of 5/4 is the same thing as root 5 over 2, like that. Okay. So all the numbers I can factor out are pi times root 5 over 2, and then I integrate that from 0 to 4, and all I got left is x dx, which of course integral x dx is x squared over 2. So this is going to give me pi root 5 over 2 times x squared over 2, evaluated at 4 and 0. The 0 won't matter, so you're going to have pi root 5 over 2 times 4 squared, which is going to be 4 squared is 16, divided by 2 is 8, so I'm going to have 8 root 5 pi is my final answer. So again, we have two new formulas tonight, and the surface area. So the two new formulas are the surface area formula and the arc length formula. Okay. So you want to make make a list of all the formulas we're coming up with so that you can learn them and know them. Um, so just that'll help you when it comes test time. If we look real quick at the project for this section, so let me exit here. Okay, so let's do that. I'm gonna, let's see. Can I do that? There we go. Share, where's stop the share area? Okay, screens. Let's see, Thomas. If we go to the, I guess, the modules, and I assume you all see this, right? Yeah. And we go to the project 2, and I can preview. So last time we talked about a whole radius root 3. This is all things. So tonight we have find the volume of the solid generator revolving the region bounded by the grass, y equals e to the minus x squared, and so forth. So that's a rotation. Yeah. So find the length of this curve from 1 to 3. So there's an arc length problem. Find the area of the region bounded by the curves y equals x. So that's just an area between two curves problem. And then here is find the surface area of the cone frustum. So cone frustum is like you have a cone and you chop it off somewhere above the bottom, so doesn't come to a point. It's like part of a cone. So generating when you rotate this from 1 to 3 about the x-axis. Okay. And then next time we'll talk about we'll do some more examples of surface areas next time, and we'll also talk about work, how to compute work with integrations, and then fluid forces, and that would be all the application stuff we would look at. Okay. So I don't know where class will be next time. I'm kind of thinking it'll be in the classroom, but if not, we'll do this same thing. Are there any questions? Good. All right. If there are no questions, we'll call it a night. Be careful out there. Don't slip and fall or nothing like that. And I will see you guys on Thursday. Mm-hmm. All right. Guess that's it for now. Good.